All right, so material for today. We are going to talk first about the equivalent circuit for an induction motor. Then we're going to talk about power. Then we're going to make the equivalent circuit a little bit less of a pain in the ass to use. And then we're going to wrap things up. So we're going to start by looking at what's going on with our stator. And actually, I need to make a note here that this is a per phase model of the stator. So there's technically going to be 3 of these, and they're all going to be electrically excited 120 degrees out of phase with each other because we're dealing with 3-phase systems. Okay. So first thing I'm going to put here is some terminals. So this is the voltage that we are applying to the stator. And then I'm going to have some resistance RS that will be the resistance of the stator winding, and I'll write this stuff down here in a moment. Then we have a reluctance JX sub S, which is the reactance of our stator winding. Then we have our shunt branch. So the resistance of our core per phase. The magnetizing reactance of our core per phase. And then over here on the far right-hand side is I'm going to have our induced voltage, ES, like so. We're dealing with RMS phasor quantities. I'm going to label a couple of currents now. So this is the current that's flowing through our stator windings, IS. This little current is I sub E. So that's our energizing current. We have our current flowing through the core, and then the current required to magnetize our core like so. And all of these voltages and currents are at our stator frequency, right? So whatever frequency we're exciting the stator at, we should see all of our voltages and currents are at that same frequency, okay? So just to label things here, RS is the resistance of stator windings. So effectively, it's taking care of our copper losses, or I squared R losses, because our windings have some real resistance. XS is the reactance of our stator windings. So this is representing our flux leakage. RC is the resistance of our core. So this is how we're taking into account our eddy current and hysteresis losses. X sub M is the magnetizing reactance. Of the core. or actually, let's call it the magnetizing reactance of the air gap. We'll talk about it in a minute, but effectively the air gap is going to dominate the reluctance of this system. And so it's really not going to take a whole hell of a lot of energy to magnetize the core, but it's going to take a whole lot of energy to sufficiently magnetize the air gap to cause our motor to spin. And then just as a distinction here, Vs is what we're going to call our terminal voltage. Of stator windings. And so that's the voltage that we apply to the stator to cause the device to operate. And then ES is going to be our induced voltage. Of the stator windings. So this is the voltage that's effectively internal to the stator, that's going to appear across the terminals of our ideal transformer in our model. Okay. So what does this look like? Have you seen a circuit like this before? In this class, right? It's the exact same thing as a transformer. Technically, this is the exact same thing as one side of the transformer. And so largely, it's going to behave exactly like a transformer does, except for one pretty critical thing, okay? So in a transformer, our current I sub E, our magnetizing current was usually very, very small. And so because our magnetizing current was very, very small, we effectively said that, well, that means the impedance of our shunt branch here in the middle, let me just throw a circle around it, must be very, very large. And so when we had our secondary resistance and reactance, we could lump them together to form a cantilever equivalent circuit. We can't do that for a transformer because that current is actually rather large this time. So there's no easy way to lump everything together. So we're going to actually be dealing with a model where we have this branch in the middle that's kind of mess things up. And we'll talk about how to fix that in a little bit. Okay. So one consequence of that is that unlike what we saw in a transformer, the value for XM is usually small, and the value for XS is usually large in comparison to what we had in a transformer. So this is what our stator looks like. Now let's look at our rotor. So at some particular slip S, we'll have the following thing. Okay. So here's a set of terminals. So we'll have slip times E2, our induced voltage drop in our rotor. We are going to have some reactance S times XR. And then we'll have some resistance, R sub R. Okay. We'll have a current flowing through our rotor windings. That is I rotor. And our induced voltage and our rotor current will be operating at our slip frequency, FR, which is just S times our stator frequency. So we have two different electrical frequencies going on here, exactly like what we should expect. We talked about that quite a bit on Tuesday's class meeting. So just to label what quantities are, we have our resistance R2 is the rotor resistance, representing copper losses in our rotor windings. We have, oh, sorry, I say R2 there, but that should be R sub R, my apologies. X sub R is the rotor leakage reactance. Representing flux leakage in our rotor windings. And then I'm calling it E2, but I'm trying to use a subscript R for the rotor side and S for the stator side, so I apologize. ER is the induced voltage across the rotor windings. So we're going to do a little bit of circuit analysis here. So we can hopefully see, using just good old Ohm's law, that our rotor current is just going to be S times our induced voltage divided by the total impedance of our rotor windings. So that'll be R sub R plus JS X sub R, where, just to be clear here, that rotor current is expressed as a function of the rotor frequency. And if we were to look at the average power absorbed by our rotor, so I'm going to call this PR subscript CU. So this is letting us know effectively that we are quantifying our copper losses. Okay. So on a per phase basis, this should just be the magnitude of IR squared times the resistance of the windings. And I'm going to add this factor of 3 out front because we have a 3-phase system. So we're going to get 3 times as much losses because all 3 of the phases will add together. Now, the problem with this per se is that it looks like the power absorbed by our rotor is independent of the slip that we have. And that literally can't be true because the more loaded our motor is, the more losses it should have and the greater our slip should be. And this equation effectively says the slip doesn't matter, which we know physically can't be correct, right? So we are going to fix things a little bit here. So we can have our rotor current, IR. We can express that as our induced voltage divided by our rotor resistance as a function, divided by our slip, plus J XR. And this current, IR, is at a frequency of the stator excitation. So effectively, we're kind of sort of referring this over to the stator side to figure out what's going on. And now our rotor resistance changes as a function of slip, which means our rotor copper losses will now look like 3 times the magnitude of our rotor current squared times R2 divided by slip. Meaning that small slip yields large absorbed power. Sorry, I'm just looking at my notation here. I'm gonna take this off right here. The reason why I took off that comma CU is because I erroneously said that this is just going to be our copper losses, but that's not true. This is our total power absorbed by our rotor. So it's any losses we have plus any mechanical output power we have, all of that lumped together. So my mistake for R. Let me, actually, it says R2 because I'm confusing myself. R sub R. Thank you for that, Bailey. Okay. So this power right here, I'm going to write this out. Represents the total power that crosses our air gap, aka the total power delivered to the rotor. So we can actually rewrite this relationship by playing around with a couple of things. So here we have our rotor power as 3 times the magnitude of our rotor current, squiggle isn't squiggly, squared, times the rotor resistance divided by the slip. And so I'm going to express that as 3 times pi r squared. And I'm going to break out that rotor resistance divided by slip thing. I'm going to have my rotor resistance here. Then I'm going to have my rotor resistance divided by slip times a factor of minus S. So if we look at what that literally means here, I'm going to do this in a different color just so that we can see what algebra has happened effectively. So I have my rotor resistance plus my rotor resistance over slip minus S times my rotor resistance divided by the slip, which means this guy and this guy literally just cancel each other out. And I'm left with just that rotor resistance over S that I had originally. So I'm just playing around with the algebra here. The reason why is because this will let me break this into 2 discrete parts, right? So I'll have 3 times the square root of the rotor current, or excuse me, the square of the rotor current times the rotor resistance, which we already said was our copper losses. And then we have 3 times the magnitude of our rotor current squared times that quantity, rotor resistance divided by slip times 1 minus S. And so this guy over here is actually our mechanical power that's delivered to the rotor. So that our total power absorbed by our rotor is a combination of the mechanical power and the copper losses. Going back to how we had our losses and all of that kind of stuff broken out when we were looking back at electromechanical energy conversion. Now, what's interesting is that we can observe that our copper losses in our rotor is actually just the slip times the total power absorbed by our rotor, right? So if we multiplied that PR expression, the leftmost representation, by a factor of S, we literally just get our equation for our copper losses. If we multiply our total rotor power by a factor of 1 minus S, we get our mechanical power, right? So if we know what our total rotor power is, very, very quickly we can determine what our losses are and what our mechanical output power is, just as a function of slip, with really no need for any other piece of information. So taking this into account, our total or complete model is going to look like this, where I am referring everything to the stator side of the device. Okay. So here's the terminal voltage across my stator. Here's resistor RS, excuse me. JXS. RC. JXM. And I'm putting a dashed line right here, where this line represents where my air gap is located in the system. Actually, I'm going to scoot it over a smidge so that I don't run into writing something weird here. So I'm going to put a positive polarity terminal here. And so this is, sorry, ES is equal to A, our turns ratio, times ER. Let me put that dashed line back in to represent where our air gap is. Here we're going to have JXR prime. So this is our rotor reactance referred to the stator side of our device, which is just going to be A times, that's going to be A squared times JXR. Here is RR prime. And this is RR prime over slip times 1 minus S, where this whole thing added together is just R2 prime over S, so that the whole circuit is acting at our stator frequency, and R2 prime is just A squared. Damn it, I keep saying R2 and I mean RR over S. So the last thing that I want to point out here is A, right? So we've referred everything from the rotor side to the stator side so that we don't need an ideal transformer in the middle of this thing. So we just need to talk about our turns ratio really quickly here, right? So when we had a transformer, we defined our turns ratio to be the ratio of the number of turns in the secondary divided by the number of turns in the primary. Here we're going to define our turns ratio for our induction motor to be the number of turns in the stator divided by the number of turns in the rotor. Now, realistically, we will actually never know either of those numbers. We're just going to have everything either referred to the stator side or everything referred to the rotor side. So we're never going to have to actually apply that A to begin with, but I just wanted to be clear about what it represented. All right, so here is our big ugly model. Now let's talk about power and efficiency. Is it okay if I go to a new page on my thing because I don't have enough space? Shaking your head violently no while you're not writing anything down. Yeah. All right, well, I'm gonna do it. I considered his head shaking violent. All right. So this is largely going to be a recap of the power relationships that we kind of looked at the beginning of our electromechanical energy conversion lecture, just applied specifically to an induction motor, right? So on the left-hand side over here, I have my input power, and this is the electrical power at our input, right? So we know that we are going to incur some losses on the stator side of the device, right? We know for sure that we have some amount of copper losses because our stator windings are going to heat up when we pass current through them. So I'm going to depict that with an arrow flowing down like so. So effectively it's leaching away some amount of our initial input power. So here we have our stator copper loss, and a mathematical expression for this would be PS comma CU. And it's going to look extremely similar to what we had for the copper loss in our rotor, except that we're going to use our stator resistance and our stator current, right? So 3 times the magnitude of our stator current squared times our stator resistance is what our stator copper losses should be. Okay. Then we're going to have over here our core losses. I'll put our mathematical expression down here. So let's think about what these core losses might be. Okay. So effectively, core losses are represented by this resistance here, RC. That resistance RC is in parallel with our induced stator voltage, right? So I should have the voltage drop across that resistor RC squared divided by the resistor value is going to give me the power. And then I multiply that by a factor of 3 because there are 3 phases. So all of this is coming from just basic elementary circuit analysis techniques. So our core losses, P core, are going to be 3 times our stator induced voltage squared divided by the resistance of our core. And so now we're at the point where we're effectively hitting our air gap. So I'm going to put that red dashed line through here, letting us know where we're at. And I'm going to call the power at this point in our diagram P sub R. I'm going to write down up here. This is the amount of power that crosses the air gap. So that's delivered to our rotor to perform some mechanical work while also taking into account any other losses that we might have. All right, so now I'm going to have some losses from the windings of my rotor. So here we have our rotor copper loss. Which we already know. To have a mathematical expression for PR sub CU is equal to 3 times the current flowing through our rotor squared times our rotor winding resistance. And I'm going to put another dashed line here. So at this point, we figured out what our total mechanical power is, right? So this is our delivered or developed mechanical power. And now that we're on the mechanical side of things, we need to take into account any mechanical losses that we might see, which we talked about some of them earlier, right? So we might have friction and windage losses because our rotor is going to have some amount of air resistance that it sees as it tries to spin, right? So we're going to have friction losses and all of that kind of stuff there. So let's introduce those. We're not going to have any equation for that. That's just something that we're going to be told or something that we are going to measure with an instrument. And then our last loss that we may see are what are called stray losses. And these are literally just any other type of loss that's incurred that we can't really figure out where it came from. So it's just stray extra power that got lost somewhere in the system. And then finally, we have the power that's actually delivered to the shaft, which is our mechanical output power. So this is what the energy conversion looks like in an induction motor, where we're taking into account literally every source of loss that we can think of to explain why the mechanical power at the output of our device is less than the electrical power that was input to it. Okay. So from here, we can say that our motor's efficiency eta is equal to the power at the output of our system divided by the power at the input of our system, which is nothing more than our shaft power divided by our input power. And we can play around with the torque relationship that we looked at the end of class on Tuesday. And we can say that, so let's put these down here, torque relationships. So our mechanical torque, so this would be the torque delivered at the blue line in our system. Is simply our mechanical power divided by the angular frequency at which our rotor is spinning. But we know that omega m is equal to omega s times a factor of 1 minus s. Right? So that's the angular frequency at which our stator field is rotating times 1 minus the slip. Earlier today, we learned that our mechanical power can be expressed as our total rotor power times 1 minus the slip. And so that 1 minus slip over 1 minus slip cancels out. And our mechanical power, there's going to be our mechanical torque, is then just our total power delivered to the rotor divided by the angular frequency at which our stator field is turning. For the torque delivered to the shaft of our machine, that's just going to be the power at the shaft divided by angular frequency of shaft rotation, or power delivered to the shaft divided by omega s times 1 minus s. So there's no real simplification we can. So let's work an example. So let's say that I have a 3-phase 25 horsepower induction motor is connected to a 208 delta 120Y volt RMS source. Which supplies 75 amps RMS at a power factor of 0.85 lagging. When the motor is fully loaded. Its stator and rotor copper losses are 1,867 watts and 650 watts, respectively. Its core losses are 1,500 watts and friction and windage losses are 300 watts. And if I don't tell you what the stray losses are, we can assume that they don't have any impact on things here. So no stray losses to account for. I want us to use this information to determine A, total power delivered to the rotor. So this is our air gap power. B, the developed mechanical power. C, the shaft output power. And D, the motor's efficiency. So let's start by looking at part A here. So I want to figure out the total power that's delivered to the rotor. So if I come back up here to my diagram, it looks to me like the total power delivered to my rotor, which is that PR at the vertical red dashed line, is going to look like whatever my electrical input power is, minus my stator copper losses, minus my core losses. Anybody have a problem with that interpretation of our diagrams? Nope. Okay. So I'm going to write that down over here. So P sub R is going to be Pn minus P S C U put it in this way, minus P core, I think is what I had it labeled as up here. Let's scroll up. Yep. So we have our stator copper losses. That's this guy right here. We have our core losses. That's this guy right here. So my question to you guys is, how do we figure out what our electrical input power was? Voltage and current. Okay. Fantastic answer. It's missing a little bit, okay? But that's a big part of it. Our input power is going to be the average power. Okay, so all the powers that we're dealing with are real powers. So what's my average input electrical power? That's not just going to be current times voltage, because the magnitude of the current times the magnitude of the voltage is the apparent power, not the average power. So we got to do a little bit more work than that, right? So we're going to go back to our circuits relationships. So our input power for a simple single phase system would be the magnitude of my voltage at the input times the magnitude of my current at the input times the cosine of the difference between the phase angle of my voltage and the phase angle of my current, right? This looks arguably familiar. Well, we have a three-phase machine, which means we need to throw a 3 on there to account for the fact that we have a three-phase machine. So that begs a further question. We are told that our voltage source is a 208 in a delta configuration and a 120 volts in a Y configuration. Which of those voltages should we use? Well, that 75 amps RMS that's flowing into our motor is a line current, right? So that's the current that's flowing down the wire that's connecting our source to our machine. So because we have a line current, we need to use a line voltage. If we used a phase voltage, we would have to transform that current or whatever. So that's actually going to screw with our relationship just a touch here. So instead of having 3, it'll be √3, because remember from three-phase power, that average power should be √3 line voltage, line current, cosine, phase angle, right? So square root of 3 times 208 volts RMS times 75 amps RMS. How do we figure out the cosine of theta v minus theta I? So the inverse cosine of the power factor is theta v minus theta I. We want the cosine of theta v minus theta I. So that's the cosine of the inverse cosine of the power factor, which is just the power factor, right? So 0.85. I think, let me make sure yep, 0.85 lagging. So we throw this into our calculator. We should get 22.950 kilowatts. From this, the power that's delivered to our rotor is 22.950 kilowatts minus 1.867 kilowatts minus 1.5 kilowatts, which comes out to be 19.583 kilowatts of power is delivered to our rotor. Anybody have any questions, comments, or concerns about what we did here? So we're always going to be dealing with line current. So just to be really clear here, if I choose to use the delta connected voltage, I'm going to have square root of 3. If I accidentally use the Y connected voltage, it would just be times 3. We're going to be okay as long as we use the right scaling factor for our three-phase relationship either way. Okay. That's the great thing about a balanced three-phase system. All right. So now we need to figure out our shaft's output power. No, our developed mechanical power, sorry. So let's go back up here. So our developed mechanical power, our delivered mechanical power is literally just the air gap power that we just found minus our rotor copper losses. So that's easy enough. Because our rotor copper losses are right here. That's going to be 19.583 kilowatts minus 0.65 kilowatts. Comes out to be 18.993. Kilowatts. We weren't asked for it, but could we calculate the slip? Matthew, you're shaking your head. Tell me how you do it.
SPR, and you reorganize it, you have PR to use.
So absolutely. So just as a quick aside thing here, we know that PRCU is just S times PR. So our slip is literally just going to be our copper losses in our rotor divided by the total power delivered to our rotor. Right, which should be some very small number. So 0.65 divided by 19.583 means this rotor, this motor was working at a slip of about 3.3%. All right, part C. The shaft output power. So let's look up here again. So our shaft output power should be the mechanical power we just found, just minus our friction and windage losses because our stray losses were negligible. But easy enough. I'm using the symbol PFW for the friction and windage losses. So that's going to be 18.993 kilowatts minus our friction and windage losses were 300 watts, so 0.3 kilowatts. So that comes out to be 18.663 kilowatts. And then lastly, we want our efficiency, which is our shaft output power divided by our electrical input power. So that's 18.663 kilowatts divided by 22.950 kilowatts. And then we'll multiply this by 100% so that we get it as a percentage. And I got 81.19%. Yes, sir. Oh, yep, you're right. I just wrote it down. Actually, I wrote this down wrong. It should be 18.933. Which makes this 633. Yeah, so little transposed errors, but process is correct. I just can't read my own handwriting. But thank you for pointing that out, Tom. All right. So I feel like that was fairly straightforward. When we're given all of the powers and all of that kind of stuff, we can kind of figure out what the relationships are. Yes, sir, Matthew.
I have questions. How do you figure out what voltage to use, delta or Y?
So effectively, I'm going to draw a picture here of how I envision the system in my mind. And that's what guided me. Okay. So over here on the right-hand side of my system, I have my motor, which is serving as the load. It literally does not matter whether the internal connections for my motor are delta connected or Y connected. Literally, the only thing I have access to is its terminals, right? And so I was told that a current having a magnitude of 75 amps RMS was being drawn by my motor. Perfect. And then over here on the left-hand side, I have my voltage source. Right? And I was given a voltage in both a delta connection and a Y connection. So if you recall from, was it 280 last spring? Our average power in a three-phase system can be expressed as 3 times the magnitude of our phase voltage times the magnitude of our phase current times the cosine of the angle of our impedance, which that bit right there literally just means the power factor. Or it's the square root of 3 times the magnitude of our line voltage times the magnitude of our line current times that same cosine factor. Because we know that in a balanced three-phase system, the phase voltage and the line voltages are square root of 3 different from each other. I guess really that's for delta configurations. And the phase currents and the line currents are square root of 3 difference of each other in a Y configuration. So it's going to work out that way regardless of whether or not we have a Y or a delta system. I chose to interpret that 75 amps as a line current because it's the current flowing down my transmission line that's connecting my source to my motor. So I used the line voltage, which would have been the delta connected voltage, and a square root of 3. If I had chosen to use the 120, that would have been a phase voltage. And so I would have had to, I guess, kind of sort of make an assumption that my motor was a Y connected machine so that my 75 amps of current is my phase current and my line current simultaneously. Because we know that in a Y connected something, line currents and phase currents don't change. And so I could have just used 3 times 120 times 75 or square root of 3 times 208 times that 75, and I'll get the same answer either way. Yep, is which voltage we use, okay? So for me, because I don't know anything about how anything is connected, the line voltages is, line voltage and line current is the safest bet to use because we literally can't screw that up. It doesn't matter how anything is connected if we use those quantities. Yep. All right. So we're going to go back to our equivalent circuit here. So when we were told all of the powers, everything worked out pretty easily. Now let's figure out how to look at things if we aren't told all of the powers and we have to deal specifically with voltages and current, which means we have to analyze that circuit, right? Or analyze that equivalent circuit. So we are going to make a couple of quick simplifications. Okay, so we're going to start off with, let me write this out as the Thevenin or IEEE recommended equivalent circuit. So starting with my original equivalent circuit, here's my terminal voltage Vs. Here's my resistance Rs. Here's my reactance JXS. Then I have my shunt branch. So I'm going to put my dashed line here representing my air gap just because it helps me think about what's going on. JXS prime. And for simplicity's sake right here, since we're just playing around with things, I'm going to choose to lump those two resistances together. So sorry, this should be RR. This is my total rotor resistance, right? So representing copper losses as well as how much I've loaded the motor. Okay. All right, so the first simplification that we can make is to recognize that since our magnetizing reactance is small in comparison to our core losses, these two things in parallel is just going to look like the magnetizing reactance, right? Because whenever I have two things in parallel, one is very large, the other is very small, the equivalent is just going to be close to the small thing, okay? So first simplification is effectively we just throw away RC. So that's going to leave us with this circuit. RS JXS JXM air gap JXS, dang it, JXR, and I made that mistake up there too. Prime. R sub R prime over S. Now, you may be thinking to yourself, well, if I throw away that RC, how do I take into account the core losses? Because if that resistor isn't there, we have no way to keep track of it. So typically speaking, the core losses get lumped in together with the friction and windage losses and the stray losses, and we call that rotational losses, right? So rotational losses are P rotation is equal to our core loss plus our friction and windage losses plus our stray losses. So recall, just for the sake of argument, that our core losses were related to the induced voltage drop internal to the device anyway. So that's not something that we can't really measure that voltage to begin with. So that's something that we were always effectively going to have to be told, right? The things that we can measure are our currents and all of that kind of stuff that's flowing through the terminals of our devices, okay? So our core losses are still in. Now we're just lumping them together with friction and windage losses, saying that's rotational losses, which we can measure with a power meter and going on about our day. Okay. So now what we're going to try to do is we are going to apply Thevenin's theorem to the stator portion of the equivalent circuit, so that effectively we're going to try to wind up with a single loop circuit so that we don't have to wind up setting up a system of equations and all of that kind of stuff to solve this thing. Okay. So if we take the Thevenin equivalent of everything to the left of the red dashed line, we should be able to figure out some Thevenin voltage that's applied to our input and some Thevenin impedance that's seen looking into those terminals, right? So for our Thevenin voltage, this is our system. We have our voltage Vs here. I'm gonna have to rewrite my notes. Rs, Jxs, Jxm, and here's Vthat. So how do I find Vthat? What kind of circuit is this? It's a voltage divider. Yeah, so we can just use voltage division, right? So our Thevenin voltage should literally just be Vs times Jxm over Rs plus J XS plus XM. Let me erase that so that looks better. Anybody have any problem with how I applied voltage division there? All right. Now let's find the magnitude of the Thevenin voltage. So what I'm going to do to find the magnitude of my Thevenin voltage is I'm going to take the magnitude of each of those parts and effectively just combine them, right? So the magnitude of the voltage V Thevenin should be the magnitude of Vs multiplied by the magnitude of JXM divided by the magnitude of RS plus JXS plus XM. Make sense? Okay. So the magnitude of Vs is just the magnitude of Vs. The magnitude of JXM is just XM. And the magnitude of that combination, RS plus JXS plus XM, is going to look like the square root of RS squared plus XS plus XM squared. Right. So now we can make an observation. Okay. RS squared is usually going to be appreciably smaller than XS plus XM squared. So it's not really adding a lot to our expression. So we can approximate our Thevenin voltage as Vs times XM over XS plus XM. Okay. This does introduce a little bit of error, but for the overwhelming majority of induction machines, it should be very, very small. If we ever didn't want to include that error, we could just default back to this expression where we have an exact equivalence and not an approximate equivalence. So now let's look at our Thevenin resistance. Okay. So for our Thevenin resistance, here's our original circuit. Here's RS, JXS, JXM. These are the terminals that we're looking into. But whenever we're finding the Thevenin impedance, we need to be looking at a dead network, right? So a dead network means my voltage source over here is turned off or short-circuited. So what do we have? We have that impedance JXM in parallel with the impedance RS plus JXS. So that's going to look like JXM times RS plus JXS divided by RS plus JXS plus XM. Since RS squared is much smaller than XS plus XM squared, and XS is typically smaller than XM, we can approximate our Thevenin impedance as well. So our approximate Thevenin impedance will just be RS times XM over XS plus XM quantity squared plus JXS, where this part right here is our Thevenin resistance. And this part right here is our Thevenin reactance. So applying our Thevenin equivalent circuit, replacing our stator, our new model looks like V Thevenin in series with R Thevenin plus JX Thevenin. There's our air gap. Our rotor reactance referred to the stator in series with our rotor resistance referred to the stator. This is our current I2 prime, like so. I feel pretty strongly that we can analyze this thing really easily because it's just two impedances in series from here on out, right? So by inspection, or really using Ohm's law, whatever way floats your boat, we can see that our current I2 prime, so, or damn it, I keep calling it I2 when it should be I rotor. IR prime is just going to be our Thevenin voltage divided by the series combination of those two impedances. So the real part of that is going to be R Thev plus RR prime over S plus J X Thev plus XR prime. And from here, we can see that the magnitude of our rotor current is just the magnitude of our Thevenin voltage divided by the square root of R Thev plus RR prime over slip squared plus X Thev plus XR prime squared. And then that whole thing right there is square rooted. From here, we can now define our rotor power because we know what the magnitude of IR is, right? So if we recall that the power delivered to our rotor is 3 times IR squared RR over S, then that's going to look like 3 times the magnitude of our Thevenin voltage RR prime over S sorry, that Thevenin voltage should be squared And then I'm actually going to get rid of that square root sign in my denominator. So this is just going to leave us with R thev plus RR prime over S squared plus X thev plus XR prime squared. So effectively now we can determine our rotor power really only in terms of our equivalent circuit parameters. All of the circuit analysis has effectively been done for us to determine what those things are. So let's take a moment to figure out what our torques and stuff like that are going to look like as well. So our mechanical torque is just our total rotor power divided by omega S. So that's literally just going to be our exact expression that we just wrote down, except that there's another omega S distributed among the denominator, right? So 3 times the magnitude of the Thevenin voltage squared times RR prime over S divided by omega S times R Thev plus RR prime over S quantity squared plus X Thev plus X R prime squared, close that bracket off. Yes. All right. Coming in the home stretch, a couple of quick relationships that we want to figure things out now. Okay. All right. So we have an expression for our developed mechanical torque. So now let's talk about what the torque looks like at when our motor starts. So when our motor starts, our rotor is literally not moving. What is the slip if our rotor isn't moving? Go back to your notes. We literally talked about this condition. So a slip of 0 means that the rotor is moving at the exact same speed as the stator field strength, right? A slip of 1 means the rotor isn't moving. So our starting torque I'm going to write here, S is equal to 1, is literally just this expression, except that we get to get rid of all of the over S's because that's just 1. Right? So 3 times our Thevenin voltage squared times our rotor resistance referred to the stator over omega S times our Thevenin resistance plus our rotor resistance referred to the stator squared plus our Thevenin reactance plus our rotor reactance referred to the stator squared, right? So that's our starting torque. And how do you think it's going to compare to our mechanical torque when our device is up and running? We actually already talked about this, but seeing if you guys are paying attention. So one of the disadvantages of a induction motor is that they have low starting torque, right? And we can see that from this expression right here. So if our starting torque, if S is 1, this guy is going to be much smaller than when S is some number like 0.01, 0.02, 0.03, whatever, because we're always dividing by a number that's much smaller than 1, which is essentially the same thing as multiplying by a number that's much larger than 1, right? So our mechanical torque during operation is always going to be much, much larger than our starting torque. And these two relationships explicitly tell us why that is. Okay. Now, let's figure out what our maximum developed torque is. So the maximum developed torque is going to occur when the power that we deliver to the rotor is at its maximum. Because we can see that our mechanical torque is proportional to the power that we deliver to the rotor, right? So it stands to reason then that whatever the maximum value of our slip is going to tell us whatever the maximum value of our torque is, since our torque is dependent on slip, right? So effectively what we're doing is we're saying the slip, which causes maximum torque, will occur whenever the derivative of the power delivered to our rotor with respect to slip is equal to 0. So literally what that means, I don't know what you guys' math background and all of that kind of stuff is compared to, I guess a more traditional engineering student. I don't know how to, yeah. So like in the I guess it wouldn't be a pre-calculus class and all that kind of stuff, but in calculus 1, and whatever you guys' equivalent to that is, you may have learned that in order to find the maximum value of a function, you take the derivative of that function and set it equal to 0. That's literally all we're doing right here, okay? So taking the derivative of our power delivered across our air gap or our rotor power with respect to slip, setting that equal to 0, and then solving for whatever slip makes that happen. Well, not to bog you guys down with the calculus too much, but what we'll find is that PR max occurs when the rotor resistance divided by the slip is equal to, sorry, I missed the equal sign here, R thev squared plus that should have a prime, sorry, X thev minus X R prime. Where there, where at this thing. So under this particular condition, without bogging you guys down with the derivation, we find that our slip for which maximum torque occurs is given by R2 prime divided by RR. Thank you, Bailey. R thev squared plus X thev plus x2 xr, damn it, prime squared and using this, our maximum torque is 3 times the magnitude of our Thevenin voltage squared divided by twice omega s times r thev plus the square root of r thev squared plus x thev plus xr prime quantity squared. All right. There are 10 minutes left in class, and the example problem that I wanted to work has 12 parts. So we're going to do that on Tuesday as part of the review for how to apply all of this stuff. I think Bailey, your hand was.
Yeah, the PR max to the x minus x that's positive or that's supposed to be?
Right here, this is supposed to be a minus. Yes, sure. So oh, I see what you're saying there. I'll need to double check my textbook because I see exactly what you're saying. If the average power delivered to, or excuse me, if the power delivered to the rotor maximum occurs when this, then you should just be able to algebraically rearrange that to get this relationship right here. So either that negative sign is wrong or this negative sign is wrong. I would be willing to bet that negative sign is wrong. I will make a point to double check that, but my money is on that one being incorrect. And the reason why I say that is because it doesn't really make a whole lot of sense to have a negative sign there unless you're trying to get those reactances to cancel out. And there's literally no way that's going to happen in an induction motor system because there's not any capacitance to do that. So I would say I'm 85% confident that one's supposed to be a plus sign.
Oh, okay, you said our homework is Saturdays, but can't because it on Sunday.
Sunday. The later day.
Drink.
Yep. Okay, good deal. All right. Hopefully I haven't bored you guys too much. Like I said, we will work some example problems and then review stuff on Tuesday. So we're done with material for the exam. So work on your homeworks, come to class on Tuesday with questions, office hours, all that kind of good stuff too. Thank you guys for putting up with my bullshit.